So if I continue this integral, we have 2 pi, integral 0 to 1, and then root, geez, we still have this ugly thing out here, times, now let's go ahead and take the square root. Can I do that? Can I go ahead and just talk about what that would be right now? What would I have on top? e to the x plus 2, and on the bottom, what would I have? Well, we would have a square root of 4, which would be a 2, right? So we'd have a 2 on the bottom? 2, and then what else? The square root of, Yeah, they made the problem very nice for us, didn't they? Yeah, and then also look at this. This 2 and this 2 cancel also. So at the end of this just turns out to be like pi integral 0 to 1 of e to the x plus 2 dx. And that we could do with relative ease. Antiderivative of that's just itself. Antiderivative of that's 2x. Just plug in 1, plug in 0, we're done. Dot, dot, dot. Okay? All right. Let's do another one. For the next one, I want us to do x equals 1/3 y squared plus 2 to the 3/2. And for this, we want to look at y being between 1 and 2. We want to find the surface area, rotate about the x-axis. So if we are going to do this around the x-axis, we have a formula we have to use, right? 2 pi integral y ds. We get to choose the ds now. Which ds version is better? The one with the x prime in it, right? The one with the x prime, or if you want the g, right? Because the g was a function of y. Why is that better? Because it's solved for x, right? It's solved for x. So if I use the one with x prime in it, so I'm thinking I'm going to be using this one. When we use that, we're integrating with respect to what? dy, right? Which means in my integral, I need y's in there, right? Not x's, y's. So when I look at this formula now, 2 pi, I can put my limits of integration. These are my restrictions on y, which are 1 and 2. It's given to us. Great. Okay, 1 and 2. And then I need to work with this. Now pay attention. This is tricky. It's tricky because it's not tricky. Do I need to do anything with this y?
No.
It's supposed to be y, right? In the previous problem, we replaced that, didn't we? We replaced it because when we were integrating, in the previous problem, we were integrating with respect to x. So we needed everything in terms of x, didn't we? But because we're going to be in terms of y, we just need this y to be a y, something with a y in it. But it is y. So it's just y. That's all it is. There's nothing else you have to do. You do not have to solve this for y. Like if I tried to solve this for y, wouldn't I get something with x's in it?
Yeah.
But I'm integrating with respect to y, so I don't want x's. So I just leave y alone. I just leave it. It turns out to be very nice. Then I have square root of, and then now let's do this part. I'm doing this over here. So what's x prime?
1/3.
1/3? 1/2, right? Right, 1/2. So this power came out, and that gives you a 1/2, and then all of that, don't change it. To what power? 1/2. subtract 1, right? Times derivative what's inside? 2y. Making sense? Good things are happening. 2 gone. So this is just y times y squared plus 2 to the half. That's x prime. I just brought this y out front. What am I supposed to do with that? Square it. All right, I don't mind squaring this. This looks pretty nice, actually, right? Because I've got multiplication here. So if I take x prime and I square it, I'm going to get that squared, which is y squared. And this is the square root, isn't it? So when I square that, it's just y squared plus 2. And heck, man, I'm not upset about that at all. That's y to the 4th plus 2y squared. Just distribute the y squared through. Then I need to add 1 to that, right? So I think I'm ready to go under the root. I'm going to go under the root right now. It's this plus 1. dy. And what's under the root? You recognize it. Okay, it's a perfect square. So this is 2 pi integral 1 to 2. Y is out here. And then you're saying that this right here really is y squared plus 1 squared, right? That's what this is. But then you're taking the square root. So we just have what here? Y squared plus 1 dy. Distribute your y through. Integrate term by term. We're done. Right? Just multiply, multiply. Y'all look confused. What's going on? What's wrong? The y bothers you? Yeah, it's a little weird. It's a little weird.
Isn't it easy? Just because
Seems too easy, doesn't it? Yeah.
the domain restriction. Is it domain or range? If it's in terms of y, that'd be domain, right?
Well, we don't really look at it that way because if we're looking at this, when we talk about domain, our domain is y because our function is a function of y, right? X is a function of y, so y is in the domain of that function.
But I mean, we didn't kind of choose this because it's the domain restriction is in terms of y. Like,
We
so it's
we
like
didn't
CP.
choose what?
Like we chose this form of the arc length formula because it's from 1 to 2 on the y-axis.
Okay, great question. Why did we choose this formula? Was it because this y was between 1 and 2? The answer is no. The reason we chose this formula was because for us, we would love to just take the derivative of x because our equation is solved for x. Okay? This is not going to dictate at all whether or not you use that one or the other one. Because I could, instead of giving you this, I could just give you, find the length of this curve, and I could give you 2 points on the curve. I could give you both the x and y coordinate of one point, the x and y coordinate of the other point. And then I say, find the length. Let me give you an example. If I gave you the curve, to make this easy, if I gave you the curve y equals x squared, and I asked you to find the length between the point 0, 0, and let's say 3, 9, okay? Then which method are you going to use? Your integral is either going to go from 0 to 3 or from 0 to 9. Does that make sense? So this is not dictating it. This is not dictating what you're using. What I would use here is I would like to take the derivative of y because it's solved for y. So I would use the one that has 1 plus y prime squared.
So just whatever it's given.
Whatever it's solved for. Maybe it's not solved for either one, though. Maybe you have to be the one to decide what you want to solve for. Now, in the problems, that's not going to happen. Yes?
That's why you're saying, like, you made a mistake of adding AB. Like, we shouldn't.
Yeah, that's why when I put AB on there, you can't have AB because you don't know if you're going to go with respect to y or x yet. That's your freedom right here. Your freedom right here is that you can decide whether or not you want to go with respect to x or y. So I can't put A and B. The reason the A, B were there is because I literally copied and pasted, forgot to erase it. Okay. Now, how do things change if we want to go around the y-axis instead? Well, if we want to go around the y-axis, what changes in the formula is not much. Go around the y-axis, the only thing that changes is x ds. So again, you have two decisions to make. Do you want to go with respect to y or with respect to x? That will depend on you. But this has to be x instead of y. And it has to do with when we wrap it around, right? A rubber band's going this way now. And so it's the radius basically this way. Okay? It's the function of y that goes this way. Yes.
So then with that one, if we use the ds that ends with dx, will we just leave it as x?
That's right. So if we wind up using the one in here that has dx on it, then we'll just leave x as x. But if we use the one that says dy on it, we're going to have to get that back to y's. But hopefully it's solved for x. So then we just replace it. We're going to do two examples here. You'll see. All right, so this one, y equals 1 minus x squared. And you know what? Just to illustrate what I'm talking about here, I'm going to do this one this way. Let's see. There we go. So we want to look at that, and then surface area about the y-axis. Surface area about the y-axis. So because it's y-axis, you need to know that you're using 2 pi integral x ds. X ds, not y ds. Now what?
So then,
You have a decision to make, right? ds, do you want it to have the dx out there or the dy out there? Dx, because this is solved for y, right? This is a function of x. So we want to be using the formula that's going to look like this. It's going to be integral, let's see, do we know what our limits of integration? Are they going to be a, b, or c, d? We're going with respect to x, right? That's what you said? So it'll be a to b. And it's going to be x, and then square root of 1 plus, which one squared? Y prime squared, and then dx. So we chose to want to take the derivative of y because it's solved for y, and that meant that this was going to be an integral with respect to x, which is why we're using a, b, and not c, d. And we know, do we know a, b?
yes, 0 to 1.
That's a, that's b. So if we had chosen the other way, it would be 1 to 0, right? Which would be weird because that would be backwards, but that's okay. All right, we need a derivative. What's the derivative of this? Negative 2x. Okay, not bad. All right, derivative squared. 4x squared, still not bad, right? And then I need to add 1 to that. All right, I'm willing to do that. 2 pi integral 0 to 1, you told me that was a and b, x root 1 plus 4x squared dx. No perfect square anymore, no trinomial thing, right? Unfortunately, we can't do that, right? And this isn't, you don't do the root of each one separately, right? Because there's addition. So what now? What do you mean factor? What?
Can you multiply the x through and square it? Or?
You could multiply that x into there and square it, yeah, but I think you're working too hard. We're going to take it back. Way back. Way back. Oh, back further. Back further.
So
U sub.
Basic.
Basic U sub. There's U, right? What's the derivative of that? 8x? You have x, don't you? You're just off by 8. So this would be just a basic U sub problem. That's way, way back. Equals dot, dot, dot. So I'm not going to do that. Got it? That one worked out. That would work out pretty nice. I'm not going to take it the rest of the way. Let's do the last example. Oh, you know what? This last example, I'm not going to do this last example. I'm going to do something else. Oh, man. Maybe I have to. I don't know.
Surprises. It's Halloween.
Scared.
Put a cube in there.
Okay. I'm going to do it. I'm going to do it this way. A little different because of time. I've been pretty impressed with us as a class that we've done a lot of things with this circle of radius r. We've shown a lot of things about this, right? We verified that the area is pi r squared. We've shown that if you take a solid ball, right, radius r, that the volume is 4/3 pi r cubed. We showed last class that the circumference of a circular radius r is 2 pi r. One thing we have not discussed is the surface area of a sphere, or the surface area of a ball, have we?
Yeah.
We haven't done that, have we? So perhaps we could just go about the same way. What we've been doing is we've been taking like this first arc right here, this little first quadrant part of the circle. You know, we found the area under it, and then we multiplied by 4.
Right.
We rotated around the x-axis, and then we doubled it to get the volume. So, and then last class we found the arc length. I forgot how we did that. But did we just go from 0 to r? I think we did. Anyway, it doesn't matter. How would I find the surface area of a sphere using that piece? So I want a sphere, right? That's supposed to be a radius, r, right? So how do I find the surface area of that using that little first quadrant arc? What could I do? What's that? Use what we're doing today.
So, I mean, function would be the section.
Solve for y or x.
Okay, so take that little blue curve, solve it for y or for x, and then wrap it around where? It wouldn't matter, the x or the y-axis, wouldn't, right? If I wrap that blue thing around the x-axis, I could find the surface area of that, right? And then double it, because that would only be half of it. Or I could wrap it around the y-axis, and it would still double it to get the surface area, right? So I'm going to do something kind of different. I'm going to take that equation, x squared plus y squared equals r squared, which is our general equation for the circle. I'm going to solve it for x. We have not done that, right?
Right.
I'm going to solve this for x. If I solve it for x, I get root r squared minus y squared, don't I?
Right.
That's a weird r. And I'm going to find the surface area about the y-axis. And the reason I'm doing y-axis and not x-axis is because I've only shown you one example of going around the y-axis. So now here's your second example of going around the y-axis. Okay? So what formula must I use if I'm going to go around the y-axis? 2 pi integral x ds. All right. I have solved this thing for x, which means that I want to use the ds that has what in it? The x prime in it, right? X prime in it. That means it's going to be d dy, right? So let me write that down. I'm going to go this. I'm going to leave x. I'm going to say this is going to be the one that has the x prime in it, and that means it's got to be with respect to y. So again, what? Huh? The points would be C and D. And C and D are y, right?
Yeah.
So my C and D that I'm using are the points here, which is 0, up to here, which is still r, right?
Right.
So I'm going to be going from 0 to r. Everything in this integral has to have the variable y in it, doesn't it?
Right.
That's x, though, which means that we need to replace this with y's. But look at my equation. This has y's in it, right? Now r is a constant. So I'm going to have to replace that with the square root of r squared minus y squared. But I still need that, right? Let's work on this part right now. So what is the derivative of x with respect to y? What's the derivative of x with respect to y? 1 over 2 root r squared minus y squared times negative 2y. So I'm doing derivative of the square root of something is that. Derivative of what's inside with respect to y is this, because derivative of r squared is 0, because r is a constant. And then this 2 and this 2 cancel. Negative y over that root. Right? I'm supposed to square this. When I square a negative, it becomes positive. Ooh, and when I square that, it becomes that. Not x, y. So square the root on the bottom, it goes away. That's not so bad, right? I'm supposed to add 1 to that. I'm going to do that down here also. 1 plus y squared over r squared minus y squared. Common denominator? So I'm going to put r squared minus y squared right there. Then plus y squared. Oh, look at that. Look at that. Those y squareds are going to cancel. And all I'm left with is r squared over, my goodness, I can see where this is going, is that, right? That's what's going under the root, and I'm real happy about that. I'm not quite sure I'm happy about the root of that, but I'm happy about the root of that. But I am actually happy about the root of that because, yeah, do you see it? What's x going to be? What's x going to be replaced with? That. Do you see what's about to happen? This is going to be awesome. Okay, so look, time to go to the integral. Okay, integral 2 pi, integral 0 to r. Now x, because I have to have y's in it, has to be replaced with my equation with x, which is this root of r squared minus y squared, but then times the square root of this, right? And so let me do the root on top and bottom here. So root on top just gives me r, and root on the bottom gives me, well, the root of that. And then they cancel. dy, right? dy? Bam, bam. That is really nice to see that happen. Because I don't even have y's left. All I have is an r, right? And that r is a constant, so it can come out. 2 pi r, right? Integral from 0 to r of what? 1 dy or dy, right? So what is the antiderivative of 1 with respect to y? It's just y. So this is 2 pi r y, and we're evaluating at 0 and r. So I replace what with r? Replace y with r first. So that's 2 pi r squared minus, replace y with 0. 0. This is half of the surface area. So what happens if you double it? And you can look that up in a book. That's the formula. 4 pi r squared is the surface area of a sphere of radius r. Pretty cool, huh? Yeah. So we've shown some pretty cool stuff. The thing I've always found amazing about math is, you know, you look at all these we're not done, by the way. All these formulas, you know, they just didn't like fall out of the sky, you know. Like every one of these formulas we had to generate somehow. All of them. Now, I took a little more time in this class than I did in my other class. I don't think we're going to get to something I wanted to do. So I'm going to have to think about that over the weekend, how I want to handle that.
We're talking about how 0.99. Wait,
Wait, weekend. What day is it? Yeah, weekend.
I think we should. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0.99. 0
That didn't take that long, did it? I still wouldn't have had time. I need like 20 minutes to talk about what I was going to talk about. Okay, real quick. I'll show you. First of all, one last little application of a classic problem, usually introduced in a calculus sequence. It's this idea of what's called Gabriel's horn. So if we take the function 1 over x, it looks like this. It actually goes up this way, right? That's what 1 over x looks like. But we're just going to consider it from 1 to infinity. Right? Now, we have not ever done this before, but imagine if you could, wrapping this around the x-axis. Okay? That should have a volume, yes? But this thing is tapering off and it's going forever. So this is like an infinite, well, Gabriel's horn comes from like horn that you play, I guess, whatever. This is Gabriel's horn. I think Gabriel's an angel, whatever. So this is his horn. It goes forever this direction, okay? So what would happen if I said, hey, wrap this around the x-axis, find the volume? You would go integral, so here's the horn, right? Here's the horn. You would go integral, pi, right? Pi, integral from 1 to infinity. So it'd be an improper integral. So you'd start at 1, never end, right? Then you would take the function and square it. So this is like outer radius squared minus inner radius squared. The inner radius squared is 0, right? So if I square that, I get this. I just brought it up so that I could do the antiderivative. The antiderivative of that is that. And then I'm supposed to take a limit here, but I think you can understand the idea that I'm going to be letting something here go to infinity. So what happens if I let that go to infinity? That goes to 0. Yep. So if I let that like this, that'll go away. And then if I plug in 1 into here, I'll get a negative 1, but then I already was subtracting. So at the end of the day, I get pi. So if you take the function 1 over x, wrap it around the x-axis, start at 1 and go forever, the volume of that solid is pi. With me? Okay. What about its surface area? Well, how would we do the surface area? We would need to take the derivative of the function, right? 1 over x. Take its derivative, so I already did that, there it is. Then we need to square it, which would give us this. And then I would do 2 pi, 1 to infinity, then this would be y, okay, y in the formula, and this would be my ds. So y is the function itself, square root of that, and then I'm integrating with respect to x. This integral is very difficult to do. So I want you to consider something. I've never asked you to think of this before, okay? But consider this expression right here. This is the surface area, right? If you believe all this. Would you agree with me that this value right here has to be bigger than 1? Why?
You're adding 1.
Well, this is 1, right? And you're adding to it some number. Because that's to the 4th power, this has to be positive, right? And remember, x is between 1 and infinity, so we know that this is going to be a positive number. It's going to be a large positive number. So no matter what, this is positive, yes? Yeah. So if you add a positive number to 1, it's a little bit bigger than 1. And if I take the square root of that, that's still bigger than 1. So any number bigger than 1, if you take its square root, it's still bigger than 1. So you all agree that this is bigger than 1? Yes? Okay, so that means whatever this integral spits out, right? It's just adding up a bunch of things, right? It's adding these things in there. If these are bigger than 1, then if I took that out completely of the integral, I would just have this, wouldn't I? Right. This integral should be smaller than that integral, because this piece is bigger than this 1 that's right here, yes? Right. See the logic behind that? So this integral is smaller than that integral. If you'd like, you could say this integral, the surface area of this, right, is bigger than the surface area of this. Now, what's nice about that is I can do this. I can do this integral. And if I do it, what's the antiderivative of 1 over x? Natural log. And if I do that, and then do my limits or whatever, and do infinity in here, what you get is divergence. You get it that it goes to infinity. And so what we're saying is that this integral right here is infinite, and the integral that represents the surface area of Gabriel's horn must be bigger than that or equal to it. Well, equal, you can't be equal to infinity, but you can be, this means this has to be infinite also. All right? If you're bigger than infinity, then you are infinity also.
So it's kind of like getting the answer through an approximation.
It's not an approximation, it's a comparison. So if we ever have an integral that we don't know how to do, if we can find a nice integral to compare it to that we can do, then as long as you're solid about how this relationship is working, then you can draw a conclusion. Now, we have to be real careful with that. If we had that instead, and this was infinite, it wouldn't tell us anything. Because all we'd be saying is our integral is smaller than infinity. Which could be anything, right? It's the fact that the inequality works that we have to be bigger than infinity that forces that to be infinite. Now, this is a famous problem. Why is it a famous problem? Think about the two results we just found. Surface area is not only bigger than the volume, it's infinite. So it means that if you had this Gabriel's horn, if you could like turn it vertically, you could go get some paint and you could pour in exactly, pi, quarts, or gallons, however we're measuring this. You could pour it in there, right? Pi, last little drop, boop, and it would top that thing off, okay? That's the volume of that. But it's impossible to paint the surface of it because you would have to have an infinite amount of paint. So this is called Gabriel's paradox. And we're not going to talk any more about it. I just wanted you to see it, okay?
But how come?
We're not going to talk about it. Go look it up on YouTube. Go Google it, all right? Yes,
Isn't Gabriel's horn the horn that's supposed to be played for the apocalypse or something?
perhaps. I don't know that part of the story. I don't know anything about Gabriel. So as far as I know, it could be just some dude. I don't know. But I'm pretty sure it's the one you're referring to.
But aren't you disregarding that it's like infinity times infinity on the surface area? Like I don't.
Infinity times infinity.
Yeah, like when you just do.
Here's the best explanation that I've heard of this. Do we agree that the volume was finite? Pi? So let's say I have a big clump of Play-Doh, all right? And let's say that this Play-Doh is exactly pi. Okay? Let's just say that's how much Play-Doh I have. The volume of it is pi. If I start rolling this Play-Doh and make a long tube out of it, it has a certain surface area, right? Okay. If I start rolling it thinner, it's going to have more surface area. Agreed? Now, the volume is never changing because I have the same amount of stuff there. Right? Does that make sense? But you could roll it flatter and thinner, and you could get infinite surface area without changing the volume. Look, it's a paradox, okay? It's supposed to cause problems in your brain. Now, the thing that we are not getting a chance to cover here is in section 7.6. In 7.6 in the book, there are more applications for antiderivatives. Specifically, the book talks about three things: how we can use calculate what's called work in physics. We use the integral to calculate work. We can also do hydrostatic pressure and force. That's another physics engineering concept. And then they also cover in this section centers of mass and moments of inertia. So I let my other class choose what they wanted to do, and we decided to look at moments of inertia and centers of mass, and we went through that yesterday. It took us about 10-15 minutes. So what I plan on doing is maybe next class I'll start with that. I'll just show it to you really fast. We'll spend 10 minutes on it. It's just to expose you to something. That's it. Application. The thing you need to understand is that, yes, I could talk about work, but the thing is, I could talk about 100 different things that you could do with integrals. So picking one thing is hard to kind of, because everyone's going to want to see something else. But I have a take-home quiz for you. This quiz will be due a week from today. Next Wednesday. Yeah, I'm giving you a lot of time, and I'm not quite sure why I'm doing that, but The idea is that I want you to stay on top of your homework. Don't fall behind on your homework. Did I give you all the homework for 7.3 last time for shells? I did, right? Okay. So do your homework also for 7.4 and 7.5. And then this, I just want to read through these instructions. I know you can read. For all the problems, set up the integrals. Do not evaluate them. I just want to see what the integral is. Include a detailed sketch for each problem. So every single problem, I expect to see a picture. The better your picture is, the more likelihood that you're going to get full credit. All right. If you turn in a thing with just answers, then I'm going to take off points. I want to see something. Do your work on separate paper, but put your final answers on this, and then staple your work to the back. All right. I give you a region that's bounded by two curves. You have to actually find their intersections algebraically, by hand. All right? You can use a computer or calculator to verify your answers, but somewhere on here you need to show me algebraically that you could set those curves equal to one another and solve. Okay? Any questions? Yes?
Can we just draw one graph?
Include a detailed sketch for each problem.
I mean, like,
For
and then after that, we can do.
For finding the region, the intersection, can you just draw a graph? Is that what you're saying?
No. Like for this one, can we just draw one, or do you have to draw for like each one, two, three?
For which?
We only have two equations, right?
It's
Can
the
we just
same.
draw-
It's the same region for each. For every problem, we're using the same region.
Yeah. Like, can you just draw that one?
For each problem. Because I want that picture you have to include your axis of rotation. I want you to show me where your outside radius and inside radius is coming from, or where your R is if you're using shells. I want to see, yeah, so that's why it's due next Wednesday. I'm giving you more time so you can put some work into it, make nice and detailed. This will be worth 2 quiz grades. Okay?
Do you have time to some of the problems?
Can we go to my office? Yeah.
It is now a good time for you.
Yep. I'm sorry? Oh, I didn't give you one?
You gave us 3.
Oh, I'm sorry. I must have miscounted.
Extra sheets for our work if we can't fit it all on.
Oh, yeah, I don't, look, it says it right here. It says do work on separate paper.
Oh, okay.
Okay, but put your final answers below. So this is going to be an integral, an integral, an integral, an integral, an integral, an integral, an integral. But all your work is going to be attached.
All right.
Okay? With all your pictures attached. I don't need the pictures on the final, on that front page.